To all of the audience that we hope is out there, this is an exciting, extraordinarily exciting presentation. Let me get out of the way because you're really here to listen to Shep, not me. So let me first introduce myself. My name is Jim Gates. I have the pleasure of being the president-elect of the American Physical Society. I tell people I'm the most useless kind of physicist. I do mathematical physics. I've been working on things related to string theory since its birth, actually before its birth. This is the EO1 session. We're planning to go from 7 to 7:39. We're gonna have a 5-minute warning for Shep, and then we're gonna try to have a 10-minute question and answer session. The title of this presentation is Seeing the Unseeable, Capturing an Image of a Black Hole. I'd like to remind the speakers to mute themselves unless they're actually speaking. The other thing is for audience members, the network feature of the virtual meeting website via the Network for Attendees link will allow you to contact the speakers and other attendees outside of this session. So have a heads up and go look at that if you're of a mind. Now you can submit your questions for this session by using the chat feature that is part of the web browser media player used to watch this session. So if you have the live feed, that's where you send the questions and I'll see them and we'll try to make a selection for Shep. So I want to introduce our actual speaker, Professor Shep Doeleman of Harvard University. He's an incredible guy. I've actually known him for a couple of years now. Let me tell you something about his background. Shep is the founding director of the Event Horizon Telescope Project, a synchronized global array of radio dishes that reaches the highest angular resolution possible from the surface of the Earth. He led the international EHT team that recently succeeded in making humanity's first image of a supermassive black hole. He received his bachelor's degrees from Reed College and then spent a year in Antarctica conducting space science experiments at McMurdo Station on the Ross Ice Shelf. And of course, we worry about the Ross Ice Shelf these days, given what's going on down there. And with an appreciation of the challenges and rewards for instrumental work in challenging and remote locations, he returned to complete a PhD in astrophysics at my alma mater, MIT. And after joining the MIT Haystack Observatory, he developed a research program in millimeter, submillimeter wavelength interferometry and carried out observations that detected the first event horizon scale structure in a supermassive black hole. After serving as the observatory's assistant director, he received a Guggenheim grant in 2012 and moved to the Center for Astrophysics / Harvard and Smithsonian that same year. He is also a Harvard Senior Research Fellow and the co-founder of Harvard's Black Hole Initiative, the first center dedicated to the interdisciplinary study of black holes. Wow, quite a guy. Shep, you got it. You're muted.
Okay. Thanks very much, Jim. I'm going to share my screen now, and we can get going. Okay, can you see that?
Yes, it's up.
Okay, so thank you for that very warm introduction, Jim, and it's really a pleasure to be here to speak to an audience, and I'm not quite sure how many of you there are, because I can't see you, but really wonderful opportunity to talk to you about this project called the Event Horizon Telescope. It's an ambitious project, it was a visionary project, and at the outset, we asked ourselves, is it possible to really see what a black hole looks like? We wanted to capture an image of a black hole. I'm the founding director of the project, been working on it for many years, but the results I'm going to present to you today are really on behalf of the full collaboration, which is worldwide. And we started off with the premise that if we could see a black hole, really truly see it, then we could test Einstein's theories at the black hole boundary, at the most extreme of our cosmic laboratories. That's where you want to go to see if the fundamental theories that we have come to believe in really hold. And more than that, we could see how black holes form the engines in the centers of galaxies that drive outflows that can change the way the night sky looks. And to do that, we had to build a new kind of telescope. So I'm going to tell you a little bit of background on that, and then also how we did it. So I'm going to start off on motivating us by looking at this galaxy. This is Hercules A. This is an optical image. And it looks like a nondescript galaxy of fuzz in the middle there. And it's about 2 billion light years away. And at the center of it, we think there's a 4 billion solar mass black hole. And the best evidence we have for that is when you look at it in the radio. And this really shows you something else. So the radio photons coming from this galaxy tell you a story that the optical photons do not. You see jets of material leaving the very center of this galaxy at near light speed. The energy contained in those two jets is equivalent to about 3 billion supernovae going off. And the extent of that jet from end to end is about 1.5 million light years. So something is driving these outflows on scales that are much larger than the galaxy itself. And the best engine that we know of to do that would be a spinning supermassive black hole at its core. And the Event Horizon Telescope wants to zoom in to the point where we can see the hot gas around the black hole and see its effects at the very center of this galaxy. Now, I want to start motivating this further by talking about gravity and Einstein. This is a public talk, so I want to bring everybody up to speed on where we are with gravity. To the left there is one of the protagonists of this whole field, Einstein, and he gave us a geometric way of understanding gravity. Instead of the Newtonian concept of matter exerting force on other parts of matter, he said that matter deforms space-time, and then within that deformed space-time, matter moves. And one of the fundamental predictions of that was that light would be bent by a certain amount. And one of the fundamental uh, experiments that he proposed was to look for the apparent motions of stars behind the sun during a total solar eclipse. As you can see at the bottom here, even though the star's true position might be behind the sun, it would deviate from its true position to an apparent position by a very small angle, 1.7 arc seconds, or about 1/2000th of a degree. And that exact deviation was predicted by Einstein. And this was all done in 1915. And then in 1919, Eddington led expeditions to view this eclipse, and they corroborated Einstein's exact value for the deviation of the starlight. And you can see here the horizontal bands showing the locations of these stars that they used to determine this. And overnight, Einstein became a household name. And really, our concept of gravity and how the universe works changed overnight. And now here we are over 100 years, just over 100 years later, thinking about doing the same kind of experiment, but around a black hole. Now, speaking of black holes, Carl Schwarzschild, just the following year after Einstein came up with his theory of general relativity, or his theory of gravity, he solved Einstein's equations during World War I. And most importantly, he did it on the front lines of World War I. I know that we are sitting in our homes now, practicing social distancing. It's a difficult time for people. And whenever I think I'm having a hard time of it, I think of Schwarzschild solving Einstein's equations in the trenches of World War I. And then I realized I don't have it so bad. But he solved it in the following way. He said, if you have a compact enough object, there would be something called an event horizon, a point around that object where the force of gravity would be so strong that light could not escape. And the formula for that is up at the top of the slide there. It's 2 times Newton's gravitational constant times the mass of the object divided by the speed of light squared. And that is the radius beyond which light can escape. But within that, light is trapped. So the idea of a black hole was born there, but it was really more of a theoretical construct. So the question is, can we make a black hole? And there are ways we can look at extremes of matter and we can start to walk towards a black hole. So on the left, you see what we call a white dwarf. And this is what our sun will turn into after it dies. It is basically an object that's the mass of our sun, but the size of the Earth. So it's held up by quantum forces, not by the forces that, let's say, form the table that my computer is on or your iPhone or something like that. It's quantum degeneracy pressure that holds that white dwarf up. And if you had a teaspoon of Earth, it would weigh, a few grams. a teaspoon of a white dwarf, of course, would weigh as much as a car. So it's extremely dense exotic matter, but it's nowhere near dense enough to be a black hole. The next contender would be a neutron star, and that's in the middle there. And that's what happens when a more massive star goes supernovae. And there, what's left is a cosmic cinder that's a few times, or maybe one or two times the mass of our sun, but only the size of a city. And that is such a dense material that that same teaspoon would weigh about 1,000 times what the Empire State Building does. So it's a completely different order of magnitude there. But it's still not enough to be a black hole because the buoyancy of the neutronium prevents it from collapsing further. When you get a more massive star, then nothing can really stop that central core from collapsing on itself. There's no stiffness of matter that can prevent all the mass of the star from collapsing into a single point. And that's when you get a black hole. That's when Schwarzschild's mathematical construct becomes reality. And we now know that there are some stellar systems that seem to exhibit those stellar mass black holes. And of course, the LIGO detection of merging stellar mass black holes really confirmed this. So now we know there are stellar mass black holes. Now, we also think that there are black holes at the centers of most galaxies. And these are of a completely different variety. These are millions or billions of times what our sun, the mass of our sun. And you see here the Milky Way, and you can see this if you get to a place where there isn't too much light pollution. And if you zoom in by a factor of about 100,000 to the center of our Milky Way galaxy, you see these streamers of hot gas funneling into the center. And at the top there, at the very center, is a white dot, and that is radio emission. Radio waves coming from what we think mark the position of a 4 million solar mass black hole, a black hole that weighs 4 million times what our sun does, and is being fed by those streamers of gas. And we know this now because there are some wonderful results in the infrared from different groups, Andrea Ghez and the Keck UCLA group, and Reinhard Genzel and the Max Planck group, which show orbits of stars around an unseen mass. That central star symbol is where we think this 4 million solar mass black hole lies, and we now have multiple orbits of stars. This is just incredible from an astronomical perspective. This is the only place you will see stars being tossed around like planets. And this all but confirms the fact that there must be a supermassive black hole in the center of our galaxy. And yet, we haven't seen it. We haven't gotten close enough in order to see the strong gravity effects that would lens gas around that black hole. Now, what would we see if we could really get up close and personal to this black hole? Well, you'd see something that we call the black hole silhouette or shadow. And this was first simulated by Jean-Pierre Luminet in 1979 based on calculations from Bardeen in 1973. And they asked, what would it look like if you had an orbiting disk of material around a black hole? And it turns out that light from the far side of that disk is lensed up and over the black hole. I'm not sure if you can see my cursor here, but it comes up and over the black hole. And then some comes down below the black hole. And so you wind up getting this circular feature here on the right that we call the black hole shadow. And the diameter of that shadow is equal to the square root of 27 times Schwarzschild's radius. So that handful of constants that I showed you before, the diameter of this feature that we should see if we could look into the heart of a galaxy is the square root of 27 times that radius. And a lot of work has been done early on by the people on the left here, Bardeen, Luminet, Falke, Takahashi, Broderick, and Loeb, and then others have started to do a lot of work theoretically on what these black holes would look like. But the idea here is that we now know what the size of this strong lensing feature should be as the black hole bends light around it. And I can't resist showing this. This is a wonderful picture that was sent to me by Jean-Pierre Luminet. He hand drew this on Canson negative paper using India ink. Every point here represents a point that he determined through a simulation on an early computer. And then, as if that weren't enough, he made the first moving simulation. of this black hole. The faint trace you see here in the faint line you see at the very center here is in fact the last photon orbit. That's the point where light orbits the black hole in a circle. Now, the state-of-the-art simulations, show something a little similar, and what I'm showing you here is actually what we think we would see if we could look into the heart of one of these galaxies. This is some wonderful work being done at the University of Illinois group by George Wong, Ben Prather, and Charles Gammey. And you can see here that photon orbit, that very circular feature that stays constant. And you also see the rotating gas circularizing around the black hole. And it's important to note here that what you're looking at are radio waves. It turns out that radio waves are special in that they can be born close to the event horizon of the black hole, and they can still free stream through the hot gas that's fighting its way towards the black hole, through the interstellar medium, through intergalactic space, through the Earth's atmosphere to our telescope. So it is the preferred wavelength if you want to get very high angular resolution images and simulations of these black holes. So to understand how light is bent around the black hole, I want to show you this animation. You'll see the black hole identified here in red, the gravitational potential shown by the deformed space-time below it. And we'll see how light is bent around the black hole from the hot gas that surrounds the black hole and what it looks like at the Earth as shown on this screen. So you see photons from around the gas and around the black hole are lensed, and you wind up seeing here at the Earth that feature that we just saw with the simulation. Again, you see the photon orbit and the gas around it, and it's at this distance here that we would hope to measure. So if we could lay a ruler across space-time, that was the goal of the Event Horizon Telescope, and measure the size of that ring, we would be able to determine not only that Einstein's gravity was valid at the event horizon, but also we could measure the mass of the black hole because of that equation you see there at the bottom. So where can we do this? Well, we could try to do this towards the center of our own galaxy. As I just explained to you, there's a 4 million solar mass black hole there. But there's a second source at the center of the Virgo galaxy, M87. And let's take a virtual tour there now. We start here in Chile, and we go towards the Virgo constellation, and we'll go through 55 million light years of distance between us and that galaxy. And the first thing we're going to see is the outer parts of this galaxy, shown here in the radio. And as we zoom in, we'll see the same kind of jets that I showed you at the very beginning of this talk emanating from the center of this galaxy. So you see there on the right, the jet extends all the way out, about 3,000 light years. And every time we get a finer detail picture, we see that jet again. And the question that we asked ourselves in the Event Horizon Telescope project is, could we see what is in this central core here? Could we resolve that? Now, this is the best image that we had made previous to the Event Horizon Telescope of this object. So you can see the beginning of the jet, you can see the northern part of the jet, the southern part of the jet, and what we didn't know was, and we didn't have the resolution to determine what the structure was at the very center, what we think this black hole is, in the center of this black square. Now, without further ado, I'm going to tell you what we saw, because I think that over 1 billion people saw this image already. So I want to share with you this image that really stunned our whole collaboration. And I think it's fair to say that a lot of people around the world were pretty taken with it as well. And it can't be understated what you're seeing here. You are seeing light being bent around a black hole. And that is, we believe, the photon orbit. You're seeing the point at which light orbits the black hole. And importantly, you're seeing a brightness on the bottom part of this image. And that's due to the fact that the gas is moving around the black hole at relativistic speeds. And when gas is moving towards you, most of the emission from that gas comes in your direction. So on the bottom, you're seeing some gas coming towards us. And the reason the top is fainter is that that's where the gas is moving away from us. So not only can we tell uh, that Einstein's prediction is correct here, and that we're seeing this ring of light, and then we can measure it, and as I'll show you later, to get the mass, but we're also corroborating all the simulations that have been made over the past decade or so, which indicate that we should see some asymmetry due to very fast gas motions around the black hole. So this was really a wonderful moment, and more the than even the science results, it shows the way forward. We'll be able now to open up a whole new field of precision measurement of black hole event horizons now, making this image sharper, extending the capabilities of the Event Horizon Telescope. And I'll tell you more about that in just a little bit. So now I want to talk to you about how we did this and what is required to make a telescope that can see this and how we made the images. So if you want to photograph a black hole shadow, you need incredible magnifying power, incredible resolution. The size of the feature you just saw is 50 micro arc seconds, and that's equivalent to seeing an orange on the moon. And there's no telescope that we had before the Event Horizon Telescope that can image that kind of feature. Now, the equation that's relevant here is that the smallest size we can see on the sky is equal to the wavelength of light you're observing divided by the telescope size. So if you want to see something that's very, very small, you can either look at very short wavelengths, or you can look at very large, you can use very large telescopes. And as I said before, we have to see through the Earth's atmosphere, the interstellar gas, and the hot gas near the black hole. And radio waves of 1 millimeter wavelength are able to traverse all those challenges, and they are generated copiously at the event horizon. So it's kind of a Goldilocks situation in which there's one wavelength in which we can see the black hole, and all those photons can come to us. The problem is that the telescope size you need, if you go through the equation at the top there, is 10,000 kilometers across. So we need to build an Earth-sized telescope. Now, normal telescopes, of course, look like this, and they have a parabolic shape to them. And the incoming radio wave from a black hole bounces off that parabolic surface. And the surface is aligned so that the whole radio wave reaches the focal point at exactly the same time. So they can all be combined, and that's where you put your camera to make an image. But the angular resolution of a dish like this is only about 5 arc seconds. You see on the left here the large millimeter telescope in Mexico, which is 50 meters across. And when you observe at 1 millimeter wavelength, it's only about 10 times better than what we can achieve with the human eye. So we needed to make a telescope much larger than this. And we do this using a technique called short wavelength, very long baseline interferometry. It sounds like a mouthful, but all we're really doing is we're combining information that we gather using radio telescopes at different points on the Earth. And then we're combining them to make a telescope as though we had one that was as large as the distance between the participating telescopes. So light comes from the black hole, and we receive it at these different radio telescopes, and we use atomic clocks that only lose 1 second every 10 million years. And we record all the data on hard disk drives, and they're time tagged with high precision. And then we transport all of that data to a central supercomputer facility called a correlator. We combine them, and those two telescopes then give you one data point. It's as though those two telescopes give you one silvered piece in an Earth-sized mirror. And the amounts of data that we're talking about are so large that we have to pack them into hard drives, into crates, and ship them via airplanes. You still can't beat the bandwidth of a 747 filled with hard disk drives. And that's how we ship our data around. So the key point here is, though, that two telescopes widely separated essentially give you one bit of information. Now, two telescopes is not enough to make an image. So we spent the better part of a decade with our international colleagues and with experts from around the world assembling an array of telescopes. So you see here the submillimeter telescope in Arizona at the top, the large millimeter telescope in Mexico, 2 telescopes in Chile, the APEX telescope and the ALMA array. In Spain, we have the IRAM 30 meter, and we have one in the South Pole, of course. And then the 2 telescopes, the submillimeter array and the James Clerk Maxwell telescope in Hawaii. Together, these give us enough virtual silvered pieces in the Earth-sized aperture that we were able to start to consider that we might be able to make an image. But even with all of these sites, even with these 8 telescopes, it wasn't enough. And thankfully, the Earth does some of the work for us. And you can see on the left here that as the Earth rotates, it changes effectively the position of all of our telescopes. And each pair now is shown connected by that red line. And on the right, you see the effective Earth-sized telescope that we're building. And every time 2 telescopes come into view, you see 1 red dot there. And over the course of an evening, it traces out an ellipse. And you can think of that ellipse as being a silvery strand of our Earth-sized mirror that's essentially reflective. And when we fill in enough of that aperture, when we fill in enough of this telescope, we're able to make an image. So the name of the game here is to get as many telescopes as we can and to wait for an entire night of observing so that we can fill in this virtual telescope. So we spent a long time getting this array going. I can't stress enough the incredible amount of work by a very, very dedicated team that went into this. I'm just going to give you a couple of the highlights here. One of the big lifts in this project was to get the large millimeter telescope up and running as part of the array, and we did. You see to the right here, one of our graduate students, Gisela Ortiz, at the telescope. She's adjusting the atomic clock. And then we got the APEX telescope working in Chile as part of our array, and you can see here in the plot a very strong spike indicating very good detections between the APEX telescope and the South Pole telescope. And here's the South Pole telescope with that same detection. It was a great deal of work went into getting that telescope up and running for to join the array. And then here's the IRAM telescope in southern Spain. And in the inset here, you see a very strong spike again in the red, indicating very strong detections to Chile from Spain. So we got all of these telescopes working, but there was still something that was missing. It turns out that at these short wavelengths, the dishes have to be very smooth. If you have a rough dish, that decreases the efficiency of the degree in which you can receive radiation. And so the surfaces of these telescopes have to be very, very smooth, and that means they have to be relatively small. We can't use the largest radio telescopes on the surface of the Earth. We have to use the smoothest ones. So we put a premium on increasing the bandwidth of our systems. In other words, we recorded very large bandwidths of the radio spectrum to make up for the fact that our dishes were smaller than at other wavelengths. And you can see the development that went into this here. On this graph, on the y-axis, you see the recording rate per station. This is the amount of data we're recording at each of our EHT sites. And on the x-axis here, you see the year. And you can see that over almost 2 decades, we increased from about 1 gigabit per second, which is a fair data rate, up to 64 gigabits per second. And the blue curve here is Moore's law. So by using commodity off-the-shelf technologies and building our astronomical instrumentation from those tools, we were able to keep up with Moore's law. On an average EHT run, we recorded 3.5 petabytes of data, which is equivalent to about 5,000 years of MP3 music. And of course, the reason we have to ship them around by plane is that if we wanted to get all that data back from the South Pole, it would have taken us 25 years by satellite to beam it back. So everything came together in April 2017. We got time on all the biggest telescopes. We had an 8-station array with all the sites I described to you. We had 10 days of observing, and we triggered 5 days when the weather was good. And I'll tell you, the weather was spectacular. It turned out that we observed many days in a row to the point where we were all exhausted. But we were successful. We got detections to all 8 of our participating telescopes. Now, I want to share with you the process of starting to look at these data, because when you've been working in this field as long as a lot of us have, you can start to look at the raw data and get a feel for what's there. So what I'm showing you here is the energy that you get when you compare the recordings from 2 different telescopes. And on the x-axis, you see the distance between those telescopes. So as you move your telescopes closer or farther apart, you get more or less energy. And you can see kind of a characteristic bouncing shape here. It comes down, it bounces once around 3.5 gigalambda, comes up again, and then bounces again around 8. Now, if you had a very simple structure, let's say a blob that I'm showing you here, you would not be able to fit these data. Okay, that showed that this dotted black line shows the best fit curve for something that was very simple. So we knew it had to be complex. You can try to fit it with a disk kind of feature, and that will fit the first null here, the first bounce, but it will not fit the second bounce. Then you can start to look at a ring structure and you begin to get very excited, right? Because now you're seeing that maybe something that looks a little bit like a ring would fit this. And then when you see something that looks more like a crescent, a little brighter on one side than the other, then you start to get a family of curves that fit this. So when I first saw this and when other members of the team first saw this, we knew there was something very exciting in these data. And then we had to image it. And we had to approach this very carefully because we were observing something that we had never seen before. We were observing something with an instrument that we really had never used before. So we were in a situation where we thought we were getting very, very good data, but we didn't have a template of past successful observations to compare to. So we split ourselves up into 4 teams. And the reason to do this was to avoid bias. We didn't want groupthink to start affecting how we were doing our imaging. And these are the 4 teams that we split up into. I really want to emphasize again, this is a big team effort. We had 4 teams from around the globe, roughly split in terms of geographic locations, but also in terms of the kind of algorithms they were using and the kind of approaches they were taking. So very independent, and we didn't let anybody speak with anybody else. So each team was very independent. And I like to describe this in the following way. It's very difficult to tell the difference between labradoodles and fried chicken. So you might think that you're looking at a labradoodle when in fact you are looking at fried chicken. And if everybody sits and thinks that they're looking at a labradoodle, they can convince themselves of that until they take a bite out of it and it tastes good. And if you think this is very difficult, imagine the difficulty trying to tell the difference between chihuahuas and blueberry muffins. So it was very important that we split up into teams and took the whole process of scientific verification and rigor extremely seriously. So this all came together on July 24th, 2018, and all 4 teams unveiled their images. And it was really a wonderful moment in our collaboration because all the different teams that used different algorithms, different approaches, different measures of goodness of fit came up with the same general feature, this ring feature. And that's when we knew that it was most probable that we had seen this long sought shadow feature. And I want to again show the group here. This is in the sub-basement of the Black Hole Initiative at Harvard, and we've been together for a week here, loving every minute of it. And this shows one of our final images on the screen there. And what you don't see here, which is important to note, is that there were an equal number of people on a speakerphone, all enjoying this moment with us, and that was very special.
5 minutes.
Okay. So we also then tried to make these images go away. So we trained our algorithms to work on things that were not ringy. So for example, we trained the algorithms on filled disks or doubles, and we made sure that they were trained on those alternative structures, then we set them loose again on the M87 data, on the data that we had. And at that point, these are the final images that we got with 3 different techniques, and you were all getting the same basic structure. So this is when we realized that robustly we were detecting this ring feature that Einstein had predicted 100 years earlier. And then more than that, we got 4 different days of data. So it wasn't just 1 day of data for which we have these results, but we have 5 separate, completely independent days of data. And as you'll notice, from April 5 and 6 to April 10 and 11, the bottom part of the emission shifts a little bit to the right. So we think that we're also seeing some dynamical evolution of the gas flowing around the black hole. And that is a completely different dynamical process that we hope to study in the future. Now, how important are these sites? Well, very important. So in the future, as we want to add more sites, we really need to think about expanding the geographical locations. This is the best you can do. This is the best you can do with a single baseline, shown here between Mexico and Arizona. It's only when you start to add outrigger sites down to Chile, you can start to see finer resolution features. And then when you add outriggers to Hawaii, you can start to see the ring. But it's only when you get all of the sites that can see the Virgo A galaxy that you begin to see that ring. And what about Earth rotation aperture synthesis? This is the technique we're using where all the data as the Earth rotates are combined together. So on the left, you'll see the Earth rotating. In the middle, you'll see that virtual plane filling in. On the right, at the top, you'll see all the data being added to that plot that I was showing you before. And then on the bottom, you see the 3 different techniques and the best image they can make with the cumulative available data. And you can see that as you wind up collecting all the data when the Earth rotates, you get better and better images. So it's the combination of all of this that gives us these high fidelity images that corroborate Einstein's theories. Now, how do we extract the mass from this? Well, we can measure the diameter of this ring. And this is an algorithm that was made by a few people. I'm showing here a graphic by Dom Pesce, who's one of the postdocs who works with us. And you can see that as you trace this ring, you can look at the thickness of the ring at the bottom and the radius. And this then can be compared to that square root of 27 that I was showing you before. There's a lot more that goes into this, of course. There's a huge amount of data analysis. There's a huge amount of precision and fitting work that goes into this. But by equating the size of this ring with the distance to this galaxy, we were able to extract a mass in a way that astronomers had never been able to do this before. And we got a mass of 6.5 billion solar masses with an uncertainty of only about 10 to 15%. And this has been compared with other methods of getting the mass of this galaxy. And we were unraveling and answering some mysteries about the other methods of getting this mass. But this really is the best mass we feel for this galaxy, done by laying a ruler across space-time and using Einstein's equations to get the mass. So if this kind of business didn't make you feel small before, this kind of puts it in perspective. It's a wonderful cartoon by XKCD, and you can see that our entire solar system fits well within this ring here, which shows the event horizon. The reason this image is dark in the middle, of course, is because light that goes past the photon orbit is forced to spiral in and disappears forever through the event horizon. That's why that part is dark. And it's about the same size as the farthest person-made object from the Earth, Voyager 1. Now, the question I get most often is, what's next? And what's next is that we want to build a next generation event horizon telescope. You can see here in yellow all the points we have so far. We're adding some new points in orange, the Greenland, in France, and also in Arizona, potentially new sites in red here. But we want to add all the sites in blue now to roughly double the number of stations. And when you do that, the filling in of the Earth-sized virtual array is so good that we can make exquisite images in the future. So what you're seeing here is in black everything that we had earlier, or everything we can do now. If we increase in frequency, if we go to higher frequencies, then we can add all of the information you see here in red. And if we add double the number of stations, we get everything in the blue here. So we begin to almost fill in that Earth-sized aperture. Now, what does that mean? Well, it means that we can start to study in detail the link between the black hole and the jet. On the upper left here, you see a simulation of the black hole in the inset and how it launches this low surface brightness jet. This is very faint emission. This is just as the jet's getting going. In 2017, we would never have been able to image that jet. That's what's shown here in the center. But with the next generation instrument, we can get such exquisite imaging that we can start to study exactly how the black hole launches these jets.
Shep,
Yeah.
I hate to interrupt because this is like a great mystery story. I love it. But we have very strict rules about time, and you are at time if we're going to allow any sort of byplay with question and answer. So can we?
Okay. I from the time I started talking, I hit my timer. It's only 36 minutes. I guess maybe we had a overall limit.
Well, we were also instructed about a Q&A. That's the problem.
Okay, so I'll tell you what. I'll just finish up real quickly then. How about that? Okay. So I'll just also say that we want to extend the reach of the EHT into space, and you can see here if you had space here on the right, you could fill in that Earth-sized aperture very, very quickly and make movies. And when I say movies, I really do mean movies. This is where we're headed in the very near future. A movie on the left through simulation, the EHT plus one satellite in the middle. And if we had even more satellites further from the Earth, we could make real-time black hole cinema. And that's where we're headed. I want to emphasize again, this was a team effort. We started small with about 20 members. Now we have over 200 in 60 institutes, 20 countries and regions. You truly need a global team to build a global telescope. And it's had quite an impact around the globe. Nobody was shocked more than us when we came down from our hotel rooms after the announcement on April 10th, 2019 to see it was on the front cover of all the major newspapers around the world. It's been a great inspiration to us, and we hope it's been a great inspiration to you too. Thank you very much.
For those of you who would like to express your appreciation, there's a function at the bottom of Zoom called reactions. You can either give it a thumbs up or a clapping signal. Okay, I'm really sorry to have to break into this story because this is like magic, Shep. And first of all, of course, we congratulate you on your vision, your drive, and just the amazing result that we have gotten. Okay, so I've got some questions. Oh my God, I've got lots of them. I'm going to try to make a selection, Shep, and then throw them your way. So one question that I got, everyone's thanking you for the talk, by the way. I see tons of claps and thumbs up. So you should know that you have a very appreciative audience out there. Okay.
Sounds great.
We had over 1,000 viewers.
Oh my goodness. There you go, Shep. Superstar. Superstar.
It's really a pleasure.
Okay. So one question that we got looks as follows. Where is it? I'm sorry, this screen is jumping around here, unfortunately, because there's so much input coming in. Every time I try to freeze it to read. So why is the movement of the Earth around the sun not considered as the contribution to the baseline, but just the spin of the Earth?
Oh, that's a great question. So it turns out that in order to make this technique work, we need to record the data that we see at different radio telescopes instantaneously. So I think what the questioner is asking is, could we let the Earth move around the sun and then get an even longer baseline that way? But we need to be able to record the data at both those locations around the orbit simultaneously. So we can do it on the surface of the Earth with an array of telescopes in real time, but we would have to have an alternate Earth on the other side of the sun in order to do that, to get there an Earth orbit size baseline.
Another question, is Sagittarius A star harder to observe because the EHT has to look through the galactic plane uh, towards the black hole?
Yeah, great question. It is because the ionized gas between us and the galactic center can make the image a little more fuzzy. But the real reason that we're still working on the Sag A star data, which we have, is that Sag A star evolves 1,000 times more quickly than M87 does. With M87, we can wait for a whole evening and combine all the data, and the image doesn't change. But Sagittarius A star can change on a timescale of minutes. So for Sagittarius A star, we have to create algorithms that can reconstruct almost video. And that's causing us to be a lot more careful. We think we're going to be able to get results on that in the near future, but it has been more challenging than for M87.
Another question is, what are the implications of your observations for constraining or eliminating modified theories of modified or alternative theories of gravity? A theorist like me loves that question.
Yeah, that's a great question. It turns out that because the distance to M87 is not extremely well known, it's only known to within about 10 to 20%. That's one of the limiting factors on whether the size of this ring is a perfect match to Einstein's prediction. So we can only test Einstein's theory at this point to that level. We are waiting, of course, for Sagittarius A star data, where we know the mass exquisitely well, and we know the distance exquisitely well. That would be a much stronger test of different forms of gravity.
And looking towards the future, we have the question, what is the timeline for the next generation data taking and imaging?
Not fast enough. we aim to have the design of the next generation array done in the next few years, probably 4 years, building another 4 years after that. And I'm pretty confident to predict that we will have first black hole movies using a next generation instrument before the end of this decade.
Okay. There are lots and lots of kudos and congratulations to you, Shep. Please convey to your team how much this audience of over 1,000 people was in love with the work that you did and the dedication and pushing science to its very limits.
It's deeply meaningful to get that. I mean, we do think of ourselves as being explorers, and that we made a virtual expedition to this black hole 55 million light years away. And it's our absolute pleasure to come back and report back what we've seen.